And when the pack is married to the body shell of the vehicle, it completes the safety cell for the occupants. In fact, it provides a safety cell for occupants and battery cells. It's a safety cell for cells as well. But it also significantly enhances the structural rigidity of the car, making the car better handling and more refined. And it really stabilizes this central structure for the crumple zones at the end of the car to work to absorb energy. Now, also, you may note, if you're eagle-eyed, that we've actually turned these modules, and it applies to all the modules, kind of upside down. We've got the electrical connections at the bottom and the cooling at the top. There's a reason for doing that. We allow the cells to vent downwards and away from the occupant for safety. And also we have this extra layer of coolant here to give more safety. And let's just take a look at how this system works if we move to our 18-module pack here. And we see that this is matched to these vents, which allow hot gases to emerge from the pack outwards and away from the occupants to buy time in the event of a thermal event. Now, also, a key safety feature here of this pack is this ballistic shield, which is 8 millimeters thick, and it is an advanced epoxy composite. But this is not just performing a role of safety, it actually has an efficiency function as well, because this composite undershield is actually curved. We've created a wing car with a curved undertray to give extraordinary aerodynamic performance, to enhance efficiency and range. This is the synergy, the synergistic approach that we've taken to engineering even key safety features within our battery enclosure. So this is where we lead to our modular construction of our battery pack. And for many years now, we've been the sole supplier to the World Championship single-seater electric race series through our old brand, Ativa. And this is one of the modules that powers those racing cars. It's extremely high-tech, state-of-the-art, and we've accrued so much learning from this endeavor. And the wonderful thing is we've been able to transfer that knowledge, that DNA, across to this. This is the mass-producible, cost-effective cousin of the racing module with all the knowledge integrated in it. And this is the module which forms the heart of the battery pack for Lucid Air, and actually will be for Project Gravity in a couple of years' time. So this is a Lucid Air battery module. And you see inside there we have 300 of these 21700 cells, 300 per module. And we string 22 of these modules together to achieve the 924 volts of our long-range pack, and we string 18 of them together in series to achieve the 756 volt pack, which is good for over 400 miles range with the foot garage. On one side, you see all the electrical connections with this bus bar, which is a signature patent of Lucid. And on the other side, you see the cooling manifold, which allows a water glycol coolant from these inlet and outlet here to run round and cool this module. So I mentioned that we string 22 of these together, and each of them has 42 volts. So we string 42 volts times 22 modules together to get the 924 volts. And each of these modules have 300 cells. So we multiply by 22 and we get 6,600 cells. And in the case of the Grand Touring, that gives us a total pack energy of 112 kilowatt hours. And in the instance of the Dream, slightly different cell chemistry, we achieve 118 kilowatt hours total pack energy. Now, why should we go for high voltage like this? Many other cars are running at just 400 volts. Well, let's just explain this with some simple math.
There's a classic formula, Ohm's law, voltage equals current times resistance. And we can also link watts, power. Remember watts are power? And so power, there's a simple formula for that as well. Power is voltage times current. Yes, you just multiply volts by amps and you'll get watts. If you've got 100 volts, 10 amps, you'll get 1 kilowatt. So now we can actually substitute in this formula from equation 1. We can substitute for V and we can insert IR instead of V from equation 2 times I. And we result in this classic formula. Power is I squared R. And this is an inescapable law of electrical circuitry. And so the heat losses aren't just proportional to the current in amps, they're proportional to current squared. And this is a fundamental. And remember, power is volts times current. So we need a certain amount of power. We all want power. So if we double the voltage, we can half the current. And if we half the current, we can quarter the heat losses. This is a fundamental core tenet of Lucid's drive to higher voltage. We've partnered with Electrify America with a 1,000-volt charging network. We're using nearly all of that. There's a little bit of buffer in there with our 924 volts. And, you know, there's no substitute for voltage in terms of efficiency. Now, I want to just put to bed an urban myth about batteries. A lot of people say, well, you can charge so fast because of the high voltage. And it's partly true, but it's super misleading. Yeah, we achieved over 300 kilowatts of power in an independently conducted charging test very recently. And we've proven that with Electrify America, we can accrue over 300 miles range in just 21 minutes. This is unsurpassed. But there's kind of this myth that cells charge faster because the voltage. Well, if we look at one of these little cells here, and if I'm a dumb little battery cell like this, all I will see when I'm charging about 4.2 volts in a full charge at that end, and here I will see 0 volts. If I give it much more than that, bad stuff will happen. If I don't give it that, it won't charge very well. So each little cell, doesn't matter if the car's at 4 volts, 1,000 volts, it could be 100,000 volts. Each little cell doesn't know the voltage of the car. All it receives is its individual charging voltage, around 4.2 volts. So then you think, well, hang on. So if the cells don't charge any faster, whether the car's 400 volts or 900 volts, why are you doing the 900 volts? It's the rest of the system. It's the rest of the system that sees the benefits of this increase in the voltage. And we look at this holistically. For example, these connectors here on our bus bars are made from aluminum. They're not made from copper. Actually, although silver is the most conductive metal, and if I was going to make a money-no-object pack, silver would be my metal of choice, but there's a cost imperative at work here. Copper actually is the best if you're really limited in space, but in terms of mass effectiveness, weight advantage, aluminum is fantastic. Aluminum is the best choice, and that's why we use aluminum here in this application to keep the weight of the pack down. So, look at this, there's 300 cells, they're all wired together. I can't see how this results in a higher voltage. It's very difficult to relate the layout of this, when we see these 300 cells, to the voltage of the pack. So how do we do that? So I've got some flashlights here as a great sort of aid to understanding. And here we've got a standard length flashlight. And these cells are just 1.5 volts. So we put 3 of those together, end on end. We just connect them and put one after another. Like that. And what we have here is 0 volts, 1.5 volts, 3.0 volts, 4.5 volts, and we end up with a bulb at the end of this flashlight or torch, as I was brought up to say, which has got 4.5 volts. And lo and behold, we can go for a longer torch or flashlight, as has got 4 cells, or we can go for 6 cells. So this one will have, that will have 6 volts, and then this one will have 9 volts. Now, can you imagine, if this is 9 volts, just how long the flashlight would need to be to achieve 924 volts? I think this thing would be about, probably about 50 foot long. So clearly connecting things that way is not the smartest. We need to think of another way of connecting cells together. And also, the way in a flashlight these just touch each other end on end really is not an efficient connection. There's too much resistance here. It's not really suited to the vibration regime that's going to last a car for maybe 200,000 miles. So we need to think of a different way of doing that. And also, we need to think about each cell, each one of these, is 4.2 volts as an open circuit voltage. To get to 924 volts, you need 4.2 volts, and we need to put 220 of these end on end. And the 220 results in our 924 volts. So we'd need to think of about a column of these, or a long flashlight, super long, 220 of these on end to achieve the 924 volts. But of course, that would only give us 220 cells, which is nothing like the 6,600 that we need to achieve the energy. There wouldn't be the energy in this pack. So we have to do something as well in parallel. And that is literally put the cells in parallel. We need to create another column of cells in parallel here. And it's like really, if I were to bunch up a whole group of flashlights and hold them all together, it's like putting them in parallel to connect that way. So we need to connect in series and in parallel. And we achieve that through the way we connect all these cells together inside the module. So let me open the module up and explore. So here we have the Lucid Air module. And this reveals all the cells on end, 300 of them. And what we do is we group them in groups of 30. And we have this little membrane here as a little bit of insulation, and then you can see that the next group of 30 runs through to here. So we have 10 groups of 30 cells. And each of those steps, each group of 30 steps up the voltage by 4.2 volts. And because we've got 10, the voltage of this module is 42 volts. 30 in parallel, 10 in series. 22 of these, so we have, in engineering parlance, we would describe this pack as a 220S for series and a 30P for parallel count. That's how battery engineer would describe the long-range pack of a Lucid Air. So I'd like to just spend a little bit of time showing our cooling strategy here. We use this plate, and this cools the cells from their ends. This is an end cooling arrangement. We think this has got many advantages, thermally, and also in terms of consistency of manufacturing and cost as well. And it's an excellent way of containing and managing the temperature of the cells. In certain cold weather conditions, we need to heat the cells up. We have to use some of their energy to warm themselves. And in hot weather conditions, the cells actually sometimes need to be cooled not just by cooling through the radiators, but through the compressor loop on the air conditioning. Now, why do we choose this end cooling rather than side cooling, which is another approach altogether? Well, there's a very interesting aspect of a cell. If you look at a cell, this cylindrical layout here, it's thermally anisotropic. What does that mean? It is actually able to conduct heat in different directions at different rates. It's really good at conducting heat axially, but it's really quite poor at conducting heat sideways. You might say, well, what's that ratio? It's quite significant, actually. We have this advantage, this thermal anisotropic nature, but of course the heat has to flow a long way, and we'll get an imbalance between the temperature at one end of the cell versus the other. That's the downside. But we've got a real great advantage here. We can get a very clear, consistent area of contact on this end through a thermal adhesive that we layer on here when we close this plate off. And this is very consistent and reliable and mass producible, and consistency of manufacturing and cost effectiveness is critical in a battery pack. Now, if we take the other approach, which is side cooling of these cells, we have a configuration of cells here in a classic honeycomb. Yeah. But we have to make a little gap between them. They won't go right close together because in that configuration, we need to run a coolant channel between them down the sides of the cells. This is a well tried and tested, and it's not a bad system, and it's real pros and cons here. Now, of course, with that, we need space for that channel. So we won't be able to achieve this close, compact honeycomb that we achieve with Lucid. So here we're able to get more energy more compactly this way, but we do have a little price to pay that we have the cooling plate on the end. So the module is just a tiny bit deeper. Whereas alternatively, the side cooling means that the module, like for like, apples for apples in terms of energy, is a little bit bigger, but a little bit compact in its height. But there's a real downside to this, which is not self-evident. To try to achieve a perfect fit along the side of the cell here is extraordinarily challenging at the best of times, let alone in mass production. And you tend to get funny tolerancing effects coming in. And as a consequence of that, you tend to get, contact points. I mean, what you'd want here is a pure, perfect contact point running over a big area of the cell, like that. That is very difficult to achieve. It's more likely you get a couple of contact points, an interrupted condition. Very tricky to achieve that. I'm not saying it can't be done, but super challenging for a consistent effect. So here you have the cell not wanting to conduct heat, but the heat hasn't got to go so far. The cell does want to conduct heat, and you can have a really consistent, a flat area, but the heat's got to go further. And we've elected for that. And that's part of the reason we're getting this extraordinary efficiency. So our philosophy is to end cool the cells. This gives us a more consistent, more reliable, more manufacturable, more controllable system. And key to that is this cooling plate, this cold plate, which is just a two-piece aluminum stamping. And what you see are a lot of these dimples here, and these dimples are bonds which hold the lamination of two pieces of aluminum together to resist the pressure of the water glycol, which is pumped in and out from these unions. But these dimples provide another function. They create a turbulent effect to the water flow. The flow of water comes in here and goes right around this racetrack and then out here. So why do we want to induce this turbulent effect? And the reason is that if we induce a turbulent boundary layer to the fluid flow, it enhances the conductivity at that surface. And we want maximum conductivity. We need a fluid which can absorb a lot of heat and collect a lot of heat and transmit a lot of heat very quickly. Super cost effective, super manufacturable, and a key element of how we take a step forward to mass industrialize the electric car with technology like this, which is designed to be made
by the millions of units. That's how we're going to drive the cost down, and that's what's going to help save the planet. So last but not least is how we wire all these cells together. Remember, we've got 10 groups of 30 in parallel. Now, when we look at the flashlight, we look at the negative being on one end of the cell and the positive on the other. But there's an interesting feature of these lithium-ion cylindrical cells is that the negative comes all the way around right to the top. So let me just illustrate that. A cell here. All right. So not only is that negative, and there's the positive end there, but right round to this lip here, that's negative. And remember, we want to link negative to positive to step up the voltage. So we don't actually have to use one end to connect positive and the other to connect negative. We can actually put both connections at the same end of the cell. And that's what we do so that we can have the cooling on the one end of the cell here, and we have all the electrical connections, the positive and the negative here. And in order to span across these rows, these 3 rows of 10 cells in that series group, we have this bus bar configuration, these aluminum brush bars, and this is all integrally molded in this single shot injection molding, this entire assembly. These bus bars are not glued in, they're actually encapsulation molded in this plastic injection molding. And it's an absolute breakthrough. It's a one-shot deal. It's going to revolutionize mass industrialization of these semi-structural modules. But let me show you in detail how we do that and how our learning from our racing experience has really helped. We know that resistance in the system is our enemy. I squared R. I squared is terrible. We want to reduce resistance. So what we do is we have different gauge bonds for negative and positive. We put a thinner bonding wire here, and we put a thicker bonding wire here. I'm giving away one of our big secrets here. This is how we reduce the heat losses in a Lucid pack. To the best of my knowledge, no one else has done this. This is really proprietary stuff, and we learnt this from motor racing, because you only need 1 fuse per cell, not 2. So how dumb is it to put 2 fuses on, both of which incur resistance? We can have a thick one, which really saves us on energy and minimizes heating loss. That way we can have smaller radiators. And we put a thin one, we have to give it a little bit of resistance, lose energy, that one, but that's the safety valve. And really, that's one of the keys to making this the most efficient car in the world. Finally, a little word about our battery management system. Here, integrated into this module, is our BMS computer system, a distributed system. And what this really does is multifunctions, but I can give you just a flavor of how vital this management system is. If you look at the battery pack, we go from 0 volts at one cell through 220 steps up to 924. So what we need to do is create this staircase of voltage. And there's 220 steps on the staircase of voltage. And each one of those steps is 4.2 volts in a full charge. Now, we can have lazy cells, lazy groups of cells, and they might not all do their lion's share of the work. What we need to do with our battery management system is iron out and even out that those steps of voltages are equispaced, that we don't achieve an imbalance in the system. This is just one of the key attributes of our BMS, and really it is as much a software discipline as hardware.